Imagine flying an attack helicopter only a few dozen meters above the ground. You are moving quickly, using hills, buildings, and vegetation to stay below enemy radar. Your aircraft carries warning systems and flares designed to confuse heat-seeking missiles. But somewhere below, a concealed air defense team is watching. One soldier raises a launcher weighing around 16 kilograms. The missile's seeker begins scanning the sky. It detects the aircraft, analyzes its infrared signature, and attempts to separate the real target from the defensive flares released around it. A lock indication appears. The operator fires. Seconds later, the missile is accelerating toward an interception point, while the team that launched it is already preparing to move. This is the threat represented by the FN-16, one of China's most advanced export-oriented man-portable air defense systems. Known as the FN-16 or Flying Crossbow 16, the FN-16 was developed as a successor to the earlier FN-6. Its mission is to give infantry units a mobile defense against helicopters, low-flying aircraft, cruise missiles, drones, and loitering munitions. But how does it actually work? And what makes it more capable than older generations of shoulder-fired missiles? The complete FN-16 system. The FN-16 is classified as a fourth-generation man-portable air defense system, commonly known as a MANPADS. It was developed in China and is associated with the China National Precision Machinery Import and Export Corporation. The weapon consists of several major components. The missile is stored inside a sealed, disposable, composite launch tube. This tube protects it during transportation and remains attached until the weapon is fired. Beneath the tube is a reusable grip stock. It contains the trigger mechanism, safety controls, electrical connections, and fire control electronics. The system also uses an optical sight, allowing the operator to acquire and follow a target visually. Some export configurations may reportedly include thermal sights, night vision equipment, or an identification friend or foe system. The final major component is the battery and coolant unit, or BCU. Before an engagement, the operator connects the BCU to the launcher. It powers the electronics and cools the missile's infrared seeker. That cooling process is essential. Infrared detectors work more effectively at lower temperatures because cooling reduces internal electronic noise. This improves the seeker's ability to detect small differences in heat and separate an aircraft from the surrounding environment. After the missile is launched, the empty tube is discarded. The grip stock can then be connected to another missile canister. Although one soldier can operate the FN-16, a normal team may include a second person. The assistant can carry spare missiles and batteries, observe the airspace, help identify targets, and provide security. This matters because a MANPADS engagement may develop in only a few seconds. The most important feature of the FN-16 is its reported dual-band imaging infrared seeker. Older heat-seeking missiles generally search for the strongest infrared source in front of them. Aircraft engines produce intense heat, making them natural targets. But this creates a weakness. An aircraft can release flares that burn hotter than its engine. A basic seeker may turn away from the aircraft and follow the decoy. An imaging infrared seeker works differently. Instead of seeing only a bright point of heat, it forms a more detailed infrared picture of the target area. It can analyze the target's apparent shape, movement, position, and thermal pattern. The FN-16 reportedly operates in 2 infrared bands. This allows the seeker to compare information from different parts of the infrared spectrum. That is important because a flare and an aircraft do not produce exactly the same signature across every wavelength. They also move differently. Once released, a flare separates from the aircraft, slows down, and follows a falling trajectory. The aircraft remains powered and continues along a controlled flight path. Digital processing can compare these characteristics and attempt to identify which object is the real target. This does not mean the FN-16 is immune to countermeasures. Modern aircraft may use advanced flares, directional infrared jammers, warning sensors, evasive maneuvers, and tactics designed to prevent a successful launch. Weather, smoke, dust, cloud cover, terrain temperature, and the position of the sun can also affect infrared detection. But compared with a simpler seeker, the FN-16 has more information available to reject false targets. It is not simply searching for the hottest object in the sky. It is attempting to recognize and track a specific aircraft. An FN-16 engagement begins when the operator or assistant detects an approaching target. Unlike a large air defense battery, a MANPADS team may not have its own search radar. It often depends on visual observation or information from nearby units and external surveillance systems. Once the target is located, the operator raises the launcher and tracks it through the optical sight. The BCU powers the system and cools the seeker. While the operator follows the aircraft visually, the missile searches for a stable infrared signature. When the seeker achieves a lock, The launcher provides audible and visual indications, but a lock does not automatically guarantee a good engagement. The operator must consider distance, altitude, speed, direction, background conditions, and target identity. Engagement geometry is especially important. A helicopter moving slowly across the battlefield presents a different target from a fast jet flying away. A receding aircraft may expose a strong engine signature, but the missile must chase it while the distance continues to increase. A head-on target closes rapidly and gives the operator less time to react. Published information gives the FN-16 a reaction time of approximately 5 to 10 seconds, depending on readiness, visibility, target acquisition, and operator training. In combat, that may be the entire firing window. Once fired, the FN-16 operates autonomously. It uses a single-stage, solid propellant rocket motor to accelerate away from the launcher. Solid fuel is well suited to portable missiles because it can remain stored inside the weapon without requiring fueling before combat. After launch, the seeker continues tracking the target while the guidance system calculates an interception course. The FN-16 reportedly uses proportional navigation. Instead of flying directly toward the aircraft's current position, the missile observes how the line of sight between itself and the target is changing. It then turns to reduce that movement and establish a collision course. In simple terms, the missile attempts to fly toward where the aircraft will be rather than where it is now. This is more efficient than simply following behind the target and improves performance against crossing aircraft. However, the missile still has limited energy. Every sharp turn reduces speed. If the aircraft maneuvers aggressively, releases countermeasures, or is engaged near the edge of the missile's range, the FN-16 may be forced to make energy-consuming corrections. The FN-16 is reported to have an engagement range of approximately 500 meters to 6 kilometers. Its reported altitude envelope extends from around 15 meters to 4 kilometers. These figures describe the general engagement zone, not a guaranteed kill boundary. Actual performance depends on the target's speed, direction, altitude, maneuvering, countermeasures, weather, and the operator's position. After firing, the soldier does not guide the missile. The FN-16 is a fire-and-forget weapon. This allows the team to take cover, prepare another missile, or leave the launch position immediately. Rapid movement is critical because the flash, smoke, and infrared signature of the rocket motor may reveal where the missile was fired. The FN-16 reportedly carries a high-explosive fragmentation warhead fitted with impact and laser proximity fuses. The impact fuse activates if the missile directly strikes the target, but a direct hit against a fast and maneuvering aircraft is difficult to guarantee. The proximity fuse allows the warhead to detonate when the missile passes close enough to the target. The explosion sends high-velocity fragments outward. These fragments may damage engines, rotor blades, fuel systems, control surfaces, sensors, wiring, hydraulic lines, or the airframe itself. Against a helicopter, damage to the rotor system, gearbox, engine, or flight controls can be catastrophic. Against a fixed-wing aircraft, even a non-fatal hit may force the pilot to abandon the mission or make an emergency landing. The FN-16 is intended to protect infantry, mechanized formations, airborne troops, special operations units, and strategic sites from low-altitude threats. Its possible targets include attack helicopters, low-flying strike aircraft, transports during takeoff and landing, reconnaissance aircraft, cruise missiles, UAVs, and loitering munitions. Its greatest advantage is mobility. A MANPADS team can move on foot, operate in difficult terrain, remain concealed, and appear where an enemy pilot may not expect it. Even when no missile is launched, the possibility of MANPADS in the area can force aircraft to fly higher, change routes, release more countermeasures, or reduce the time spent over the battlefield. But the FN-16 also has clear limitations. Its range is short compared with larger surface-to-air missile systems. It depends heavily on line of sight and early target detection. Training is also decisive. The missile may be fire and forget, but the engagement is not automatic. The operator must identify the target, judge the firing conditions, achieve a stable lock, launch at the correct moment, and relocate before being attacked. The FN-16 represents the evolution of man-portable air defense from simple heat-seeking missiles toward more advanced imaging weapons. Its reported combination of dual-band infrared detection, digital processing, proportional navigation, autonomous guidance, and a proximity-fused fragmentation warhead is designed to improve performance against maneuvering targets and traditional infrared decoys. It cannot replace medium or long-range air defense systems. Instead, it forms the lowest and most mobile layer of an air defense network. a layer that can move with infantry, hide in difficult terrain, and threaten aircraft operating close to the ground. And that is the real importance of the FN-16. It allows a small and concealed team to challenge helicopters, aircraft, missiles, and drones across a critical section of low-altitude airspace. For an aircrew, the greatest danger is not always the missile already in flight. It is the launcher that remains invisible until the moment it fires.